So next is the refraction of light. So let's just remind ourselves what refraction is. This is the change in direction of energy transport as a wave, in this case the light wave, passes obliquely, meaning at an angle, from one medium into another. And so what was the key idea with changing from one medium to another? Oh, that's right. The most important thing about refraction is remembering what happens is that there is a change in speed of the wave due to change in medium, right? And it's the reason why it has to be at an angle is that means different parts of the wave change speed at different times. That's what results in that change in direction. To remind us of a couple of other things, what happens to the frequency of the light during this? Hopefully you said nothing, no change, because there's no change in source. Therefore, we could also say the period, no change, because once again, source dependent. The wavelength changes, absolutely, because if the speed changes, the wavelength is directly proportional to the speed. So as the speed changes, so does the wavelength. Amplitude changes because we said that some light is reflected. Okay, so not all is going to be transmitted into that new medium. And so that's what's happening with the amplitude. Now, remember there was two situations. There was when I slowed down, and then there was when I sped up. And hopefully we remember when I slowed down, the light bent toward the normal. And when I sped up, light bent away from the normal. Okay, that's what we had said before about refraction. So what I'm going to do is I'm going to do a couple quick demos, classic demos about this, just so that you can see it. And then we're going to look to the math of this, because that's what we said we would do. We'd layer on the math when we got to light, because the math gets a lot simpler with light. It's just cleaner. Okay, so here we go. Some demos. Let me grab the camera. Boom. I've got my glass of water here, and I have my straw. Okay, and we're focusing right there. You can see what's going on there. See how there's like a break in it? That's because the light is being refracted not only through the glass but through the water, and so it looks like the straw is broken, but it's not actually broken. It's just because the light that was coming from the water has shifted because of refraction. It changed the direction. Looking at that from the top, we're not seeing it. Well, why are we not seeing that bend from the top? Well, hopefully what you realize is that the light is coming directly up at us, meaning that the angle of incidence is 0, so there's no refraction, right? So there you go, that classic example of seeing the, you can even see right there, another different break than what's going there. Notice the shape of the surface that it's going through, whether that's the curved shape of the glass here or whether it's this faceted shape, affects the degree of refraction, which is kind of neat. Now I'm going to put the back up here. What I have here is a block of what is called lucite. It is a mostly transparent thing, has one surface of this that is made to be translucent so we can see some stuff. Okay, and I've got a laser pointer, and this is a fun laser pointer because it's our helium neon, right? Nice intense red light, but it's also got a xenon, so it got some green, which is pretty. And so what we're going to do here is I'm going to shine the laser light in through, and you can see, that's so cool looking, sorry. You can see what's happening there. Well, first off, at this surface, when the laser light tries to go into the lucite, you can see that some of the laser light is reflected, right? That's what we said, it always happens. But some of it makes its way into the lucite. And if we were to look here, hopefully what you can see is that the angle, once it goes into the lucite, is less than what it is over here if I were to draw a normal line. Let me actually super exaggerate that, and hopefully you can see that there, right? We'll look at this through some simulations as well. Really, you can see that bending. And then it gets to this surface here. You can see, I'm not sure if you can see it, but a little bit of the laser light is reflected back in, and it exits here, and I'm getting another refraction as I go from here into here, okay? Ooh, some real neat stuff going on there. And we will look at refraction. We'll come back and see what's going on with that a little bit later, but just so you can see what I'm talking about with refraction. So, paper got a little damp there. What we're going to start talking about is the math of this. In order to start talking about the math of this, what we have to understand is how does the speed change, not the mechanism of the speed changing, but like how much does the speed change by? Because that's really what the critical idea is. So let's talk about the speed of light in a material. So how do I know what the speed of light in a material is? Well, there is something, these numbers would actually be really, really big. So the speed of light in a vacuum, 3.00 times 10 to the 8th meters per second, or if we wanted to go out to many significant figures, 29987, blah, 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 blah. Like, these numbers are massive numbers with lots of significant figures and would be really annoying to deal with. So what's been created is something that's called the index of refraction. And the symbol for the index of refraction is going to be lowercase n. And this is going to be a relative measure of the speed of light in a material. Now notice it's a relative measure, so what do we want to make it relative to? Well, let's make it relative to something that is always the same. And the best thing that we can do that's always the same when we're talking about light is a relative measure of the speed of light in a material to the speed of light in a vacuum. That's the relationship we're going to do. And so it has been defined that n is equal to the speed of light in a vacuum, which is a symbol of c, over the speed of light in the material. So I'm actually just going to put V mat down here, and that's N mat, meaning something whose index of refraction is N mat would have V mat as the speed of light in that. So thinking about this, stop the video and see if you can see what's going to be true about the index of refraction as a quantity. All right, first thing that you should have come up with is that it is a unitless quantity. Why unitless? Well, meters per second over meters per second cancels out, gives you a pure number. Next, remember what we said about the speed of light in a material. The speed of light in a material is always less than the speed of light in a vacuum, meaning that the n for a material is always going to be greater than 1. But actually we're going to say greater than or equal to 1 because when the material is vacuum, I've got C over C, and that's 1, meaning, a little corollary here, n of a vacuum is equal to 1, right? And so there you go. The next thing we want to see is as n increases, the speed of light in that material decreases. Inverse relationship, pretty easy to see there. Okay, so something with an n of 1.8 is going to be moving slower than something that has an n of 1.3. I'm going to show you a list of n's in just a moment. Now, some common materials. So the next thing that we want to say about this idea is looking at some of those common materials. So on an earlier handout that I had you download the other day, on the second page of the reference table, there was this chart that was called the absolute indices of refraction. Notice indices there, that's just a plural of index. We'll come back to what this is there for. That's a specific frequency of light that corresponds with the color yellow. But let's look at these things. We have air. Notice air also has an index refraction of 1.00, but that's the same thing as vacuum. But I will tell you the index of refraction of air is not exactly 1.0, well, it is 1.00, but it's not the same as vacuum. Technically, we'll actually write this down as a 4, the N of air is larger than the N of vacuum. But we don't see the distinction until we get to about the 6th significant figure. So the 3 sig figs, air is functionally equivalent to vacuum. So let's look at some of these things. Air, Canada balsam, you might know what that is. That's a tree sap that's been hardened. So like amber, it actually looks a lot like amber. It's a translucent solid. You have corn oil, diamond, ethyl alcohol, crown and flint. Different types of glass are just made up of different types of sand. That's all that is. Crown glass is of a higher quality than flint glass. Glycerol is baby oil. Lucite is that clear plastic I was showing you before. Quartz, I assume you've seen a quartz crystal before. Sodium chloride, that is table salt. Water zircon. Zircon is fake diamond. Cubic zirconium, you might know it as. So if you look at this, let's see if we can find some patterns. So air is a gas, 1. Then you'll notice, what else do we have next? Well, water and ethyl alcohol and corn oil. What do you notice about those? Glycerol, what do you notice about those? Yeah, they're all liquids. So gases tend to have lower ends than liquids do, and then the solids tend to have the larger. And there's no absolute limit on this, but like out of naturally occurring substances, diamond is one of the ones that has the highest index of refraction, and we'll look at an implication of that later. So we can see this table. This table is going to be really useful for all of our problem solving. So let's just make sure we've got that. And so let's say, for example, I wanted to know the speed of light in water. So the speed of light in water is, we go N is equal to C over V, or actually solve that V is equal to C over N. C here is 3 times 10 to the 8th meters per second. Water has an index refraction of 1.33, a really common thing that we have light passing through. And if we throw that into our calculators, we get 2.26 times 10 to the 8th meters per second. There's many more decimal places in that calculator, but I'm not going to put calculator effluvia down because there's no point to it. All right, so those are the basics of how we find the speed of light in a material. So now, how do I predict the amount by which the speed of light changes? Well, we said that there's 2 ways of doing this. We can go speed up or slow down. Let's do a slow down example. And so here in our slowing down example, we're going to have light going from air into water. Okay, air into water. So if we look that up, N for air is equal to 1, N for water is equal to 1.33. So let's draw that. And so let's say this is the surface between the air and the water. And let's say that I'm going to have all my light rays hitting the water surface here. And I'm going to do this with the protractor. I would really recommend that you do this as well with the protractor. Okay. And let's say that I have light incident at a couple of different angles. I don't know, I'll pick a couple of different angles. We'll pick 20, 30, 40, and 50. And I'll do these in different colors. Right, so here's my 20-degree angle of incidence. We'll go green, 30-degree angle of incidence. Next color, 40-degree angle of incidence. And final color, 50-degree angle of incidence. So here we go. What we need now is an equation. And the equation that we have that predicts what's going on is something that's called Snell's law. And Snell's law says that if you take the angle, or the index of refraction of the material you're originally in, which we'll call N1, times the sine of the angle that the incident ray makes with the normal, right? So we'll call that theta 1, that's equal to the angle, the index of refraction of the material you're going into, N2, and then sine of the angle that the refracted ray makes with the normal, theta 2. Now, why am I using 1s and 2s rather than initials and finals? Well, if you think about my glass of water, oftentimes light goes into something and comes out of something. So in a given problem, I might have multiple angles, and I don't want to label things initial and final because my final might become my initial or not. And these problems get a little bit more complicated. So let's leave it at that. So what I want you to do is stop the video, and we know that we did this for a 20-degree angled instance, a 30-degree angled instance, a 40-degree angled instance, and a 50-degree angled instance. So theta 1 is equal to that, theta 1 is equal to that, theta 1 is equal to that, and theta 1 is equal to that. So what I want you to do is I want you to stop the video and use Snell's law in order to find the angle of refraction for each of these. And go for it. All right, so let's see what work that you should have had. I'm just going to fill in the template in each case, 1.33 sine of theta 2. I've got 1, because I'm going from air, theta 1, or the N1, into water each time. 1 sine 40 equals 1.33 sine theta 2. 1 sine 50 equals 1.33 sine theta 2. And then we can just go to our calculator. You're gonna have to use your arc sine button, so hopefully you are comfortable with that in your calculator. Make sure that you're in degree mode, folks. That's gonna be super important for this, okay? And hopefully what you got here is theta 2 is equal to 14.9 degrees. Okay. And going on the next one, just calculating this. Hopefully what you got is theta 2 is 22.1 degrees. Next, sine 40 times 1 divided by 1.33. Arc sine of whatever that was. Theta 2 is equal to 28.9 degrees. And lastly here, theta 2. We've got the sine of 50 divided by 1.33, second shift, enter, and I get 35.2 degrees. Okay, so if I were to draw those in, just so we get that, so our picture is complete. I probably shouldn't have put that text there. That was really silly of me. 14.9, 22, 28.9, and 35.2. Okay, so the black one went like this, and then it went here. Then we went to the green. The green went here, and then there. The blue, okay, is going to this one, and then the red is going this way, okay? And so if I just put in arrowheads there, just to show the direction, no matter what you have, there's the original ray coming in. Notice that this is closer to normal. Here's the original ray coming in. Notice the green is closer to normal. Here's the black one coming in. Notice it's closer to the normal. And here's the red one coming in closer to normal. Each time it bent towards the normal. Oh, good. That's what we're hoping when we slow down. In each case, theta 2 was less than theta 1. Awesome. So each time it bent towards the normal. Let's see also what happened. When theta 1 increased, 20, 30, 40, 50, what happened to theta 2? Oh, it also increased. So as theta 1 increased, theta 2 increases as well. So they're in an increasing relationship. But is it a direct relationship? Here, I double the angle from 20 to 40. Did that double from 14.9? That doubling would be 29.8. Nope, it didn't double. So it's not a direct relationship, it is an increasing relationship. I want you to notice here, look, I increased by 10 each time. This does not increase by 10 each time, right? In fact, the amount by which it's increasing is decreasing. Okay, I increased by 10 here. If you think about 22.1 minus 14.9, it increased by only 7.2, right? So from here to here, 7.2, going from 20 to 40, 21.1 minus 28.9, it increases by 6.8. And as you go to 50, uh, 6.3. So as theta 1 increases, theta 2 increases, but it increases in a decreasing way, right? So as theta 1 increases, theta 2 increases, but in a decreasing way. Okay? And that is fairly common Snell's law. All right, so let's look at a couple of other examples of slowing down, and then we'll look at speeding up in a different video, actually. Okay, so let's say what we were looking at is from air into water, and looking at different angles. What I want to do now is from different materials into different materials, but at the same angles. So in each case, I'm going to use theta 1 is equal to, let me turn this back to black, theta 1 is equal to 20 degrees, and we'll look at different materials there. So why don't we look at something going from air into, glycerol. We'll look at water into glycerol. We'll look at lucite into diamond. And why don't we do zircon into diamond? Just so we can see that. We already know going from air into water, our theta 2 is 14.9 or 14.9 degrees. So from air into glycerol, so that's 1 sine 20. Going into glycerol, look it up on the table, 1.47 sine theta 2. So theta 2 there is equal to 13.5. Water into glycerol, so we're going from 1.33 sine 20 into 1.47 sine theta 2. Theta 2 is equal to 18.0. Okay, lucite, which is 1.50 sine 20 into diamond, 2.42 sine theta 2. Theta 2 is equal to 12.2, and zircon into diamond, 1.92 sine 20 is equal to 2.42 sine theta 2. Theta 2 is equal to 15.7 degrees. So, what patterns do you see? So hopefully what you saw is the initial angle was 20. We know all of these answers are going to be less than 20. But notice the one that is furthest from 20, in which case the angle or the light was bent by the most. Right, that's this one here. Right, because 12.2 is most different than 20. So when did that happen? Hopefully what you're seeing is when the two indices of refraction are further apart, that the change in the direction is more. And that should make sense because remember the indices reflect something, or excuse me, talk about how fast the light goes in. This represents a larger change in speed than that does. So the idea here is the more the speed changes, i.e. greater difference in n, the greater the change in direction, meaning the greater shift that theta 2 is from theta 1. Okay, that's the basics of refraction. In the next video, we will look at what happens when light speeds up, because some sort of interesting applications occur.